We're going to look at some of the problems on your test review. It won't be all of them, but we'll go through at least one of each type to help make sure that you are prepared for your assessment over Unit 4. Questions 1 through 3 are all about solving exponential equations, which can be found on pages 1 through 3 in your Unit 4 packet. Regardless of the exponential equation, the way that you can solve is by getting the same base. You will learn of another method in Algebra 2. So the base on the left side is 16, and the base on the right side is 64. So you have to think of a way to rewrite them so that they're the same base. And in this particular problem, there are two different ways to do it. So the number 16 can be rewritten either as 2 to the 4th, or it can be rewritten as 4 squared. So those are your two options for 16. So either 2 to the 4th or 4 squared. Okay. 64 can actually be written 3 different ways. There is 2 to the 6th, then there's 4 to the 3rd, and then you also have 8 squared. So they share two common bases. So you can either use 2 to the 4th and 2 to the 6th, or you could use 4 squared and 4 cubed. What you can't use is 8 squared because 16 cannot be written with a base 8. So I'm going to use the smaller exponents, but it would work the same if you do 2 to the 4th or 2 to the 6th. So I am going to change 16 to 4 squared. And keep in mind that when you change the base, you do not lose the original exponent. So you are going to multiply that original exponent to the new exponent. So then when I rewrite 64 as 4 cubed, I'm going to multiply the cube times the 2x minus 2. And now, once the bases are equal, that means the exponents must be equal. So we are going to set the exponents equal to one another. So we are going to do 2 times x plus 3 equals 3 times 2x minus 2. And then now this is no longer exponential. You have transformed it into a linear equation, which hopefully you feel very comfortable solving. We're going to start by distributing the 2. So 2 times x is 2x, and 2 times 3 is 6. Then we're going to distribute the 3. 3 times 2x is 6x, and 3 times negative 2 is negative 6. Now we need to get our variables to one side and our constants to the other. So I'm going to move the 6x that's on the right to the left by subtracting it, because right now it's a positive 6x and the opposite would be negative. That's going to get rid of the 6x on the right. And then I'm going to move the constant of 6 that's on the left to the right by subtracting it. So 2x minus 6x is negative 4x. Negative 6 minus 6 is negative 12. Lastly, divide by the coefficient of negative 4. And negative 12 divided by negative 4 is positive 3. So for this problem, x equals 3. Okay. Number 4, you are given a description and you are trying to write a function that matches the description. So you are told you're writing an exponential function in the family of 4 to the x. So that is giving you your base. So make sure that you create a base of 4. A vertical stretch refers to the a value. Anytime it's vertically stretched, the a value should be larger than 1. So it does not tell you how much it's being stretched by. So you can make up whatever value you want. I'm just going to do 3. Because 3 is bigger than 1. All right, then we have a translation left 2. So when it goes left and right, that's up in the exponent next to x, and it should be the opposite of what it appears. So when you think left 2, you probably think -2, and that is the h value, but it's going to be the opposite, so it'll be +2. X plus 2 up in the exponent. And then finally, it's going to go up 8. Up 8 is your k value. And your k value goes at the end. It's not opposite. So if it says up 8, that's going to be +8. And that would be your function. So everything for this should be the same. The only number that might be different is this a value right here, but it must be a number larger than 1. So it could be a decimal, it could be a fraction, but it has to be bigger than 1. Most of you would probably do a whole number, and that's fine as long as it's larger than 1. Number 5 is a similar type of problem. This one says that it has an exponential function with reflected decay that has been shifted left and down. So this one doesn't really have any specifics in it, so your equation might look very different than the equation that I write, but there definitely should be some common parts to it. So I'm just going to use f of x. Remember, you can use g of x, t of x, j of x, whatever you want. The fact that it says it has been reflected means that your a value is negative. So we're going to do a -1, which is just, you won't see the ones. It'll look just like a negative. For decay, decay means your base is between 0 and 1. So you can pick any number, fraction or decimal, between 0 and 1. I'm just going to do 1/2. But you could do 1/3, 1/4, 2/5, 0.75, any number between 0 and 1 to the x. So right now we have reflected decay. It needs to be shifted to the left. In order to go to the left, that means our h is negative, but when we plug it in, because you're subtracting a negative, it will become a positive number. So it will be plus, and then you can put any number you want as long as there's a plus sign right there. So I'm just going to do 5. And then to make it go down, that means your k is negative. So negative or minus, and then whatever number you want, I'll do 7. So what our functions should have in common is they definitely should have a negative a. Your base is any number between 0 and 1. That's what gives you the decay. Your exponent should be x plus, and then whatever number you chose. And then at the end, the k should say minus, and again, whatever number you chose. 6 through 8 are examples of writing given a table. So in order to do these, we have to identify the y-intercept and the base, because they should be in the form f of x equals a times b to the x. And a is that y-intercept. So when you're looking at a graph, visually, you look for the point where it crosses the y-axis. But I don't have a graph here, so in a table, it's going to be when the x is 0. So if we look for when the x is 0, you can see our y-intercept is 4.8. So a is 4.8. So there's the y-intercept, always when x equals 0. To find our base, you're trying to figure out what number are you multiplying by. What is the pattern to get from 4.8 to 2.4 to 1.2 to 0.6? And for some of you, you can look at that and it's very easy for you to tell what it is. If it's not, that's okay. To get the base, you can take any number, any y value in your table, so I'm going to use 2.4, and you can divide it by the value in front of it, so 4.8. Make sure that you're using the y values to find your base. This would also work if you did 1.2 over 2.4 or 0.6 over 1.2, but any y value divided by the value right before it. So if you do the math either by hand or in your calculator, you're likely to get 0.5, which is the same thing as 1/2. So when you write your base, because that's a nice decimal, we would be okay with you writing 0.5, but know that it could also be written as 1/2 to the x. And make sure that that x is a clear exponent. It's not times x, it's to the x. So make sure that there's a difference. I know on the Illuminate, some of you on a problem like this picked the one where it was being multiplied by x and not an exponent of x. So just be really careful. If you're looking for more problems like this, these are found on page 18 through 21 in your packet. Number 9 and number 10 are both graphing an exponential function. So we identify the parent function, we find the parent function coordinates, we identify AH and K, then we get our transformed coordinates, and then we graph. So we will use a calculator, but it will not be until pretty much the very end, and you don't have to use a calculator either. This can be done by hand, so I'll go over both methods. To find our parent function, we need to look at the base, which is 2, and the exponent. So our base, or our parent function, is 2 to the x. Because your base is larger than 1, that makes this growth. And when we have growth, we use the values of 0, 1, and 2 for x. To find the y-coordinates, we're going to plug 0, 1, and 2 into the parent function. So make sure you plug them into the parent function. So you're putting 0, 1, and 2 in for that x. So if you do 2 to the 0, that is going to get you 1. Anything to the 0 is 1. Then do 2 to the first, which is 2. And then 2 squared is 4. So these are our parent function points. What we're going to do is we're going to manipulate those points to get our transform function coordinates. But in order to manipulate them, we need to know what A, H, and K are. So A is the number in front of the base, which is 3. And anytime your base is large, or sorry, your A value is larger than 1, it is a vertical stretch of that value, which in this case would be 3. When you vertically stretch something and make something taller, if you will, or bigger, so vertical is going to impact y. So that 3 will change the y coordinates. H. H is what is after the exponent of x. Remember that it is opposite. So that looks like a -2, but it's actually a +2. And because it's next to x, it's going to go left or right. Because it's +2, it's going to go right 2. That will impact the x coordinate because it's going right. Going right changes x. K is what's at the very end, which is -8. So our K value is -8. That is going to shift your function down 8. That will also manipulate the horizontal asymptote. So the horizontal asymptote is going to be y equals -8. Make sure you put the y equals there. And because that's going down, that's going to impact the y coordinates. All right, so I'm going to show you first how to do it without a calculator, and then we'll talk about using the calculator. I am going to go ahead and draw the horizontal asymptote at y equals -8. Remember that because this is growth and it was not reflected, in the end, our graph should be increasing and look like the picture that I just drew. It should be completely above the horizontal asymptote. You should never have points above and below the asymptote. All right, so first thing I'm going to do is I'm going to find all of the x-coordinates. So to find the x-coordinates, you're going to look at the original x-coordinates, 0, 1, and 2, and then the h value, which is positive 2. Because it's a positive 2, I'm going to add 2 to every single x-coordinate. So when I add 2 to 0, that's going to become 2. When I add 2 to 1, that becomes 3, and when I add 2 to 2, that becomes 4. So my new x-coordinates are 2, 3, 4, and that's because they shifted to the right 2. All right, now to get our y-coordinates, we're going to obviously look at our y values, 1, 2, and 4, and we're going to use the a value and the k value to get our new coordinates. So you're going to multiply y times a and then add k. So I'm going to do 1 times 3, which is 3, and then I'm going to subtract 8, which is negative 5. Then I'm going to take my next y coordinate, which is 2. I'm going to multiply it times a, which 2 times 3 is 6, and then I'm going to subtract 8, which is negative 2. And then finally, I'm going to take the last y coordinate of 4. I'm going to multiply it times 3, which is 12, and then I'm going to subtract 8, which is 4. What a lot of us did was at that point, once we had the x-coordinates of 2, 3, and 4, we went to the table, we typed in our function, we scrolled to the table and looked for x being 2, 3, and 4. But I know some of you did it manually as well, so I want to make sure I review both methods. So now we graph those 3 points. So 2, negative 5 would be here. 3, negative 2 right here. And then 4, 4. Oops, that looks more, let me fix that point. That looks more like negative 3. So 3, negative 2. And then 4, 4 right here. So again, this is growth, so it should increase as it, wow, it's a really bad drawing. Should increase as it goes to the right. It should flatten on the left towards the horizontal asymptote. All right, number 12 is a graph analysis problem. So you are using the graph to help you determine all of these things. I always suggest labeling your graph. If you need to, put arrows on the ends. The left end is negative infinity, the right end is positive infinity. I always suggest drawing the x-intercept as well and crossing out the 0 because we always use x. All right, so domain is left to right. Does it go left forever? Yes. Does it go right forever? Yes. The domain should be negative infinity to infinity. That is the domain for every exponential function. That is not a word problem. The range is bottom to top. Does it go down forever? Yes. So that's negative infinity. Does it go up forever? No, it does not. So it doesn't because of the horizontal asymptote. It actually technically goes up forever, but it doesn't go up to infinity. It goes up to the horizontal asymptote, which is at 3. Your horizontal asymptote should always be part of your range. If your function is below the asymptote, it'll be negative infinity to the asymptote, and if your function is above the asymptote, it'll be the asymptote to infinity. The x-intercept is at 1, 0. The y-intercept is at 0, 2. End behaviors. So on the end behaviors, you're describing what is happening to the function as it goes left and right. So as it goes left, we're looking at this negative infinity. So it's going left. That's why I'm writing a negative infinity. All right. What else is it doing besides going left? Is it going up to infinity? Is it going down to negative infinity? Or does it appear to be flattening? Well, as it's going left, it appears to be flattening because of the horizontal asymptote. So it is, again, it's not technically flattening, it's just what it visually looks like, but that's happening at 3. On the right end, You're looking at this positive infinity. That piece is going right, so that's why it's an infinity, but it's also going down, and if it's going down, that means your y is approaching negative infinity. All right, increase and decrease. Increase means to go up and decrease means to go down. Exponential functions do one or the other. Make sure for increase and decrease that you are looking at the x values. You're going from left to right. All right, so if we start on the left piece, which is negative infinity, and go to infinity, we are going down. So that means this is decreasing. It will never increase. So for increase, we're going to write none. And for decrease, we're going to write negative infinity to infinity. Again, it's one or the other. It will not be both. And it will not be none for both of them, because if it doesn't increase or doesn't decrease, that means it's straight and it's horizontal, which this is not. All right, positive means above the x-axis, negative means below the x-axis. Again, you're going to start at negative infinity and go to infinity. So if I start at negative infinity, right now we are above the x-axis, and we will stay above the x-axis until we hit the x-axis at 1. So it is positive from negative infinity to 1. And then as we keep going, now we're below the x-axis starting at 1 forever to infinity. So it's negative from 1 to infinity. Positive and negative should pick up where the other one leaves off. Exponential function can be positive only if it's all above the x-axis, and it can be negative only if it's below the x-axis. If there's an x-intercept, then the positive and negative interval should exist and use the x-intercept. So we said from the very beginning our x-intercept was 1, and notice we used the x-intercept in both positive and negative. All right, maximum. There is no maximum point. Don't say 3, because it never reaches 3, and that's not a physical point. So there is no maximum. And likewise, there is no minimum. Negative infinity is not a minimum. Okay? Yes, it goes down forever, but a minimum has to be a physical point. It has to be a place where your graph changes from decreasing to increasing, and that never happens because it never changes direction. Symmetry for all exponential functions is neither. Make sure you do not write none. Neither is different than none. And then f of 1 means when x is 1, what's y? Well, we actually already have that point written down, and that's the x-intercept. So when x is 1, y is 0. F of blank equals -6 is saying, all right, well, when is y -6? So you want to go down to where y is -6, and you want to look over. That's right there, and that point is to -6. It might be helpful at the very beginning to go ahead and label the points that they give you for those specific types of questions. So maybe at the very beginning, go ahead and label this point 1, 0, and this point 0, 2, and then the to -6. That way, if you see a problem like that, the values are already there, and you can just, pick the correct one. All right, sequences. So for our sequences, on number 13, it says write the recursive and the explicit rule for the sequence 528, 320, 1280. For both rules, there are two things you need to identify. The first one is a sub 1, which means the first term. Well, that's pretty easy to get because you look at the sequence and you tell me what's first, so that's 5. The other thing you need is the common ratio. The common ratio is the same thing as the base. So you can look at the numbers and see if you can tell what the multiplier is, and if you can't, it's not a big deal. To find the common ratio or the base, you take any term and divide by the term before it. So 20 divided by 5 is 4. So our common ratio is 4. This would have worked if you did 80 divided by 20, 320 divided by 80, or 1,280 divided by 320.
So the recursive rule is the one that has two parts. The first part is telling me what the first term is. So a sub 1 equals 5. And then the semicolon, a sub n equals, and then it's the common ratio, which is 4, times, and you can either use the multiplication dot or you can use parentheses. It's totally up to you, a times n minus 1. Make sure that your n minus 1, your n, and your 1 are small. They're subscript, so they should be small. If you don't like the multiplication dot, you can use parentheses around the a sub n minus 1. The explicit rule is a sub n equals a sub 1, which we figured out was 5, times r, which we know is 4, and then an exponent of n minus 1. It's essentially like ab to the x, but instead of starting at the y-intercept, which is the 0 term, you're starting at the first term. That's why that n minus 1 is there. Number 14, they give you the explicit rule and ask you to create that recursive rule. So in order to create the recursive rule, you got to find the first term. Well, that's given to you right there, -3. The other thing you need to identify is r, and that's given to you as well. That's 7 times a sub n minus 1. And again, you can use parentheses, you can use a multiplication dot, it's completely up to you. All right, for number 15, it says, since 2000, the population of the Florida panther has significantly decreased. In 2000, there were 980 panthers, and they have declined by 9% each year. Write the function p of x to represent the number of panthers after x years. Remember that our function should be in the form f of x equals a times b to the x, where a is the y-intercept or the initial value, and b is the multiplier or the base. So here it tells us to use p of x, so I'm going to make sure I use p of x. A is how many panthers we started with, which is 980. And then b is our base. Now we know that they're declining, so we know our base should be between 0 and 1. So the base is not 9. I know I said it a million times. The percent is not the base. If you are given a percent, in almost every case, there are a couple exceptions, but in most cases, if you're given the percent, then you need to first find r, which means you change the percent to a decimal. So there's two ways to do it. The correct mathematical way is to divide by 100, or you can take the decimal and move it 2 spots to the left. So your rate is 0.09. The rate is not the base. So don't put 0.09 there. Otherwise, you're going to see that they decline very, very significantly. To find the base, you need to take 1 and subtract the rate. If this was growth, you would add the rate to 1. So that will be 0.91. So p of x equals 980 times 0.91 to the x would be the function. When will there be 197 panthers remaining? So the way that we tackled this in class is we went to the table, we typed in the function, and we scrolled in the table until we found approximately 197 panthers. Remember, it won't be exact because it's declining by a percentage, which means there's going to be decimal answers. But if you scroll down your calculator, or if you're using Desmos, you can do that in Desmos. You just have to keep the table going. You should see that it's approximately 17 years. Now, when is 17 years, but what year is that? This started in 2000, so 17 years from 2000 would be 2017. So if this data is accurate, there would already be less than 197 panthers remaining. And then the last question for this one, determine the average rate of decline from 2004 to 2012. So 2004 is 4 years from 2000, and 2012 is 12 years. So your x values are 4 and 12. The easiest thing to do is to use the table in the calculator, and at 4 years, find how many panthers there are, 672, and then look at 12 years, and at 12 years, there are 316. So now that we're looking for average rate of decline, we're doing change in y over change in x. So I'm going to do 672 minus 316 over 4 minus 12, which would be 358 over negative 8, which is negative 44.5. So you're talking about 45 panthers per year. Run out of room. There we go. So it's declining by about 45 panthers per year. And number 16, it says Cooper's collection of Legos has tripled in size in the past year. He started with 15 Legos. Write the function L of x to represent the number of Legos after x years. So again, our form f of x equals a times b to the x. A is the y-intercept or the starting value, which would be 15 Legos. The base is your multiplier. It told us that they're tripling. Tripling means to multiply by 3, so our base is 3. So L of x equals 15 times 3 to the x. And then the follow-up, when will Cooper have 3,645 Legos? You can do this two ways. You can just kind of guess and check and try plugging in 1, 2, 3, 4, 5, 6, 7, and so on until you find the right answer. Or you can take your function, put it into the calculator, into the table, and scroll in your table until you see 3,645 on the y side of the table. And you should see that that would be 5 years. For number 17, in 2007, there were 1.8 million people using smartphones. The number of users can be represented by the equation a of x equals 1.8 times 1.43 to the x, where x is the time in years. Determine the average rate of increase in the number of users for the first 8 years. So you need to figure out, like, the best way to do this, the quickest way to do this is probably to go to table, type in your function, and then look for the data that you need. So when it says, and this is confusing people on the practice test and on the escape room, when it says the first 8 years, we are talking about from when it started to 8 years. So when x is 0, should be 1.8. And when x is 8, it's 31.5. So you can either plug in 0 for x, plug 8 in for x, or you can use the table and just look at the table for when x is 0 and when x is 8. Now we do change in y over change in x. So we went from 31.5 minus 1.8, and in the same order, 8 minus 0. So that gives us 29.7 over 8. And if you divide that, you get approximately 3.7125 users per year. If we round that to a whole number, because we are talking about people, although this is in millions, so it's actually 3.7125 million users per year. So I would probably leave it like that and not round it up. All right, final question. We've got a graph that represents the increase in population over the first 5 years. What is the average rate of change in people from year 5 to 10? All right, so let's look at our graph. Year 5, it looks like it is at 1,500 people. You got to be careful and look at that scale. So at the second mark, it's at 1,000, so that would mean the first mark is 500, so it's going up by 500 every time. And then year 10 is right here, which looks like it's at 3,500. All right, so change in y over change in x. 3,500 minus 1,500, which is 2,000, over 10 minus 5. So we have 2,000 over 5, which is 400 people per year. And then determine the population after 14 years. Well, go to year 14 and then go up. Oh, that did not draw that very straight. Let's try that again. All right, looks like it's right here. And go over, looks to be 7,500 people.